As you just said, my name's Alan Platt, I'm CEO of Cyberhive. We are a cybersecurity technology company and we're focused on bringing next generation cybersecurity technology to real world applications. So my background, prior to working with Cyberhive, I've got about 15 years in the robotics industry, and there's an awful lot of overlap and connectivity between the robotics industry and connected and autonomous vehicles in particular. And there's one thing that I wanted to talk about today, which a few other people have touched on, which underpins both industries: connectivity. Going the wrong way, that always helps. There we go, that's better. So as technology advances, we've increasingly seen technology underpinning a wide range of different innovation in industry. And we've heard today that connectivity is one of the megatrends in the automotive industry. So we feel that this is a really important thing to get right. And of course, there are lots of customer benefits to this. So as you can see, the kind of things that we've got here, things like over-the-air updates for vehicles. Frankly, returning a car to a dealer in order to get the software updated is a pain for the user, and it's also a complete pain and very expensive for the dealers. There are lots of emerging things like mobile applications. I've seen applications recently where you can set up the seat configuration from your house before you even go out and step out of the door to get into your vehicle. Again, connectivity underpins that. Of course, with electric vehicles, connectivity becomes even more important. It can be really frustrating to go away, come back to your car 2 hours after you've left it parked up charging, only to discover that actually it wasn't charging and you didn't know that because something had gone wrong. That's an issue that has happened to one of my colleagues at work, and it led to them missing a conference very similar to this one. And of course, even the humble key is being replaced these days. You can replace a simple key with a mobile phone, and there are many cars and applications that do that. But all of these things require connectivity, and they require technology to allow you to do that. And there are problems behind connectivity. So with advanced, complicated technology comes advanced, complicated problems. And I categorize these in 3 different areas: usability, security, and complexity, similar to ones that previous people have spoken about. So for want of stating the obvious, users do not want to use applications that are complex to set up and use, and I have lost count of the number of times that I've wanted to chuck my laptop out of a top floor window because it just simply wouldn't do what I wanted it to do when I wanted it to do it. So let's take it for read that usability has got to underpin absolutely everything else in this particular world. But security is equally important. It's often seen as the enemy of usability. The previous speaker mentioned this, in fact, that it can be seen as a major performance drag. But it's really important. Imagine what would happen if your over-the-air updates were corrupted, making the vehicles potentially dangerous. Poor security could lead to theft of vehicles if you could intercept your mobile phone, which you're using as a key. And even data flows can be interrupted, introducing privacy concerns as well as those things. And of course, in the case of autonomous vehicles and connectivity with roadside infrastructure, poor cybersecurity is just unthinkable. It could lead to deaths. It could lead to really very serious problems. And there is a security problem that's going to bring problems, and they're going to get a whole lot worse in the very near future. Some of you may recognize that image. I think this is an IBM quantum computer. We are increasingly aware in the cybersecurity industry as a whole of the threat that quantum computers are bringing. Once these hit the industry, almost all of the crypto that is widely used out there at the moment will be breakable in minutes. Now, you could argue, okay, quantum computers, they're not here yet, are they? But they're getting frighteningly close. So there's estimates that quantum computers will be available commercially inside 5 years, and for nation-state actors considerably sooner than that, perhaps even as little as 2 years. So that is an extremely frightening state for any infrastructure. And if you think about vehicles, a vehicle that's going to be developed now and may hit the road in a few years' time, that vehicle, though, the users are going to expect it to be sitting on the road and working with roadside infrastructure for decades to come. So although this is probably a couple of years out, it's a very real problem for us, and we should be working towards it now. So let's dig into this in a little bit more detail. Why are quantum computers really that much of a game changer for cybersecurity? So for those of you who are less familiar with this technology, and I count myself amongst one of those, I'm not a mathematician, and this is some very hard maths involved with this. But the way I like to think of it is you can think of cryptography generally as a lock with 1 billion keys. It's going to take you centuries to try 1 billion different keys in that lock, and it will take you a very, very long time to work through them. So to all intents and purposes, it's going to be secure. The problem is that quantum computers allow you to trial all of those different keys effectively in parallel. It allows you to do them all at the same time. And the practical way, the way this is actually achieved, is with an algorithm called Shor's algorithm, and it solves cryptography in polynomial time, and please don't ask me the details about what that means. I don't profess to be an expert in the maths, but my colleagues have told me some of the technical issues that are facing people who are dealing with conventional crypto. So firstly, there's a technique called integer factorization that can dramatically shorten the effective length of keys used by certain types of crypto, including RSA cryptography, which is very much seen as the main standard used today. HTTPS uses that. Most of the key infrastructure that we use uses RSA. It's a huge problem. There's also a technique called a discrete logarithm problem with finite fields and elliptic curves. That means that also a lot of other things, such as elliptic curve cryptography and Diffie-Hellman cryptography, are also no longer particularly useful. So to put some simple numbers on this, I mentioned RSA. 2048-bit RSA is seen as the gold standard for high security networks and systems at the moment, and for good reason, because with conventional techniques, with high power computers, it would take 13.7 billion years to break with a conventional computer. If you do that with a quantum computer running at only 10 megahertz, you could break that in 42 minutes. That's how much of a game changer quantum computers really are in this field. So in a nutshell, most of the secure comms that we rely on today is pretty much useless in the near future. So what's going to replace them? Well, fortunately, NIST, the US Standards Organization, have been working on this now for some time. And their latest round 3 has suggested actually 3 entire classes of cryptographic systems that will be safe for use against quantum computers. And they're categorized down the left-hand side here. And there are three rough areas: lattice-based, code-based, and multivariate cryptography. Again, and they each have their problems, though. So lattice-based cryptography is great, but it's really, really new. So people don't understand the full implementation and the full implications of it yet. And to give you an idea, one of the lattice-based code standards that was due to be approved by NIST was broken 2 weeks before it was due to be approved by NIST. And it was broken in such a way that you could break it with a conventional laptop in half an hour. So it was just not up to scratch. Code-based algorithms are great. They've been around since the 1970s and they're yet to be broken. But the problem is they use massive keys. The keys are 1,000 times bigger than those that we use in RSA. And so it's really hard to use those in a way that's performant in a system. And the third class there, multivariate-based, they're great for providing digital signatures, but they're not much use for actually protecting data. And providing digital signatures also, they're quite slow. So in short, it's not an easy problem to fix. There are solutions, but they're very hard to actually implement in a real-world situation. But I'm talking here about connectivity, not just cryptography. And I skirted over the third problem that I mentioned with connectivity, and that's complexity. I set about drawing a conventional network diagram, looking at the data flows for one of our customers and looking at the data flows for conventional cryptography and public key infrastructure and the associated tunnels that were generated. And after I'd finished drawing it, it looked like that. I'm sure you've all seen network diagrams that look like that. And the reality is that complexity is a real problem. So if you end up with a system that looks like that, it's pretty complex to keep it running. It can be flaky, it can be hard to administer. A small configuration error somewhere in the middle of that means that it's not secure, or it might just not work. And a single problem somewhere in the infrastructure could also break the whole infrastructure. And how irritated would your customers be if they picked up the mobile phone, tried to get into the car, and they couldn't because the server was down? Suffice to say, we think there should be a better way, and I'm pleased to say we think there is. So we set out to build a secure communication system, and the starting point was to simplify the way the data is transmitted between devices. And there's little point in making systems secure if they're so complex that users and admins just don't want to use them. So we took a think about actually what we wanted to do that would create a system that was going to be secure, but was going to meet all of the other requirements. And we had 6 key requirements that we wanted it to be. It needs to be fast, it needs to be simple, it needs to be scalable, it's got to be secure, of course. Ideally, we want it to be retrofittable, and most of all, it's got to have really good user experience. I said that's the kind of basis of everything we want to do. So we looked at solutions that are out there, and in short, there's none that actually meet all of those requirements until fairly recently. But we decided that the best way was to throw away conventional approaches, abandon VPNs, abandon conventional ways of doing things, and think about it differently. And here we set about borrowing some of the best practice from other industries, particularly remote working, and that's come on a long way very recently. And there are 2 techniques that remote working is starting to use fairly heavily. One of them is the concept of so-called mesh networking, and the other one is a concept called zero trust. So we stole those technologies and we worked out how to apply those technologies. And instead of building a classical kind of hub and spoke type infrastructure where everything communicates via central points and then transfers information off between them, we wanted to build an infrastructure where any device in the entire infrastructure can talk directly to any other device in the entire infrastructure. Cut out the middleman, basically. Why route traffic through particular central bottlenecks? What's the point? You can make things much more effective with this. Of course, we wanted it to be completely built from the ground up to be resistant to attack by quantum computer. That's critical for us. Not only that, of course, if we wanted it to be post-quantum resistant, we actually even decided to layer cryptography on top of cryptography. And that sounds inefficient, but actually it isn't the way that you can build it out. And the benefit of that is even if one of your types of crypto is broken, there's others to fall back on. So zero-day vulnerability is eliminated at source. And not only that, because we're taking these zero trust concepts and the mesh concepts and applying them, we're also able to generate a step change in performance of communications between devices. So as an example, if you're familiar with VPNs on laptops, for example, encrypted data connections can sometimes drop out. And when they drop out, it can take half a second to recover. And if you're using post-quantum cryptography, it may take 2, 3, 4 seconds to recover. And that's not really practical in our industry. We've managed to get the reconnect time, if we do see a comms dropout, down to 1 millisecond. So those numbers we were talking about earlier, 1 millisecond, that's all we need. The latency increase caused by the cryptographic algorithms that we're using, even though these are post-quantum resistant algorithms, is also in that milliseconds range. It's 1 or 2 milliseconds. Very, very low latencies, very low overheads. We also facilitate device-to-device comms, even when a central cloud service or central infrastructure is not available. So that could be vehicle-to-vehicle or vehicle-to-infrastructure. And most importantly, using this kind of concept of zero-trust networking, it allows us to build a system where everything is centrally administered. And that's critical when you're dealing with very large numbers of vehicles, because it makes administering them really simple and really, really quick and easy to do. Oh, and the best thing is it actually works. So we've built this, and we built the first demonstrators on Raspberry Pis, but they even work on embedded devices with relatively little power. And we know actually how much processing power is at a premium in some vehicles. So looking to the future, we actually believe that connectivity is going to become more important. So with autonomous vehicles, the concept of autonomous vehicles really comes alive when, as the previous speakers were talking about, you've got the ability to interact not just within a vehicle, but you've also got the ability to react and interact with infrastructure, roadside infrastructure, the ability to know what other vehicles are doing, and the ability to anticipate those kind of conditions and react to them really quickly. So with our technology, we're looking to embed applications in those areas and really secure the vehicle-to-vehicle and vehicle-to-infrastructure communications. We're looking at actually an extended application of this is we can also do application filtering so that you could use an application on your mobile phone, and your mobile phone could be completely riddled with malware, but still the application is secure and is still guaranteed, and the communications from it is guaranteed. So it would allow you to use a very dodgy mobile phone to unlock your car with a great deal of safety. And actually, similar to the previous speaker, we're also working on the cutting-edge project, trying to bring digital security by design principles to the automotive industry. And as I think as mentioned previously, this is the Cherry program, and it's backed by ARM, it's backed by Innovate UK, it's backed by Cambridge University, and actually we're working closely with Oxford University in order to implement these technologies, particularly with the communication bent and communication in mind. In fact, we're running a series of workshops with Oxford University over the course of the next few months. And the first one is on the 26th of September. And if anybody is interested, we're really trying to get into depth and actually identify what are the compelling use cases for those particular applications we talked about, what are the compelling use cases for communication, and the compelling use cases for really securing the software at a hardware level. And if you're interested in contributing to this, please get in contact with me or one of my colleagues who are around the room from Cyberhive, and my details are on the final slide. So thank you very much.